as Markus Müller from Vienna, who's going to talk about repeatable use of quantum resources. Thank you, Markus.
Thanks very much. So thank you, Camille, and the other organizers for having me. It's a pity that it's only online, but nevertheless, it's great to be at this nice workshop. I will talk about the repeatable use of quantum resources in thermodynamics. And here's a quick outline of my talk. So I will begin just to introduce thermodynamics as a resource theory, which is something that many of you will be already familiar with. In particular, on Tuesday, we already had a fantastic talk by Nelly, who was like talking about this. So what I'm saying here is perhaps a repetition of some of what Nelly said, and I want to refer everybody to her great talk for learning more about this. In the second and third part, I talk about some older work that I did. Second part has to do with a single shot, basically one particle interpretation of the free energy for states that are block diagonal. So these are states that do not have superpositions of energy levels. The third part, I will then turn to states with coherence and talk about a kind of a no broadcasting theorem for coherence, which tells you that you can, in some sense, not use coherence repeatedly as a resource in quantum thermodynamics. The last part will be about an outlook on some upcoming work, which talks about two different notions of catalysis in thermodynamics. So the first part, as I said, please recall Nelly's nice talk from Tuesday. Nelly also talked about thermodynamics as a resource theory. Let me begin by the notion of resource theory in general. What is a resource theory? So in a very brief nutshell, a resource theory gives you a set of free operations. And when you then say, well, if I have a state rho and I can transform it to another state rho prime by free operations, then you would say that your initial state rho is a more valuable resource than your final state. And here I will denote this by rho succeeds rho prime, like this greater than symbol here. So here's a famous example, and that's basically where the idea of resource theories originated in quantum information theory, in more detail entanglement theory. Entanglement theory can be in some sense formulated as a resource theory. There we think that we have, for example, two laboratories. We have Alice in one laboratory, Bob in the other laboratory. They share a pure state, psi, and then they are allowed to do only LOCZ operations. So these are operations where you can do local operations in the laboratories, and you can talk on the telephone, so classical communication is allowed, but it is not allowed to send quantum information between the labs. Now, intuitively, what this means is that you cannot create entanglement in this form. So perhaps Alice and Bob share an entangled quantum state that somebody transported to the two laboratories, but just by performing LOCZ operations, which are now the free operations of the theory, they cannot create entanglement. In fact, they can only diminish entanglement in some sense. So for example, if they are given this maximally entangled state here, phi plus, if they hold it in the laboratory, then this is a valuable resource. It's an entangled state that they cannot just create for free. But on the other hand, when you look at this product state 0 on Alice and 0 on Bob, then Alice and Bob can actually prepare the state for free, just independently preparing the 0 state. So in this sense, you can say, well, the phi plus, the maximally entangled state, is a very valuable resource. It's in fact more valuable than any other entangled state of A and B, because they can create any such state by LOCZ operations. And from any such entangled state, they can also create the product state like 0, 0. And the product states are then the useless states or the free states of the theory. Yeah, once you have set up such a resource theory with its rules of the game and its free states and operations, then you can ask more fine-grained questions. For example, in this case, you can prove something like Nielsen's theorem. Nielsen's theorem tells you exactly when you can convert an initial state to a final state via free operations. In this case, it tells you that you have to look at the Schmidt coefficients of the initial state. And if the Schmidt coefficients majorize those of the final state, then you can actually perform the transformation. You can also ask other questions, like you can ask for transition rates. given that I have, for example, n copies of a state psi, how many copies of another state phi can I create via such free operations? You can look at a phenomenon called catalysis. I will talk about more in this talk, and many other questions. Yeah? But in principle, it's really just a framework where you specify a set of free operations and free states. Now, in this sense, you can also reformulate thermodynamics in some contexts as a resource theory. Here are some key references from the early days, so to speak, when this field was developed. So this is very incomplete, but I will also talk about one of these, the third one on the list today, a bit more. Now, how can you think of thermodynamics as a resource theory? So if you first take a look at this picture here, then we have a similar situation as in entanglement theory. So we have an initial state rho of the system here, this blue state, and you want to transform it or map it into a final state in light blue, this rho prime here. And you have certain rules of the game of what you're allowed to accomplish. And in some sense, these rules of the game are the typical constraints of thermodynamics. So the first rule is that something you're allowed to do. Yeah, we always think here in this setup that there is a fixed background temperature T, yeah, for simplicity. So in this setup, that you are always allowed to introduce a thermal state at temperature T. So whatever bath you manufacture, you're always allowed to bring it in its Gibbs state gamma B. What you're also allowed to do is you're allowed to do strictly energy preserving unitary transformations on the total system. So energy preservation is an important constraint of thermodynamics, basically coming from the laws of nature. Unitarity formalizes the idea that you have fundamental reversibility of your physical laws. And what you can always do is you can basically throw systems into the bath, into the garbage bin, so you can always trace over systems for free. Now, when you write down mathematically what the set of operations is, then you find that you get a set that's called the thermal operations. So a thermal operation is a map of the form that I've put down here. You take your initial state rho, you combine it with a Gibbs state gamma, and then you do a global unitary UAB, and the unitary should commute with the total Hamiltonian, HA plus HB. So be energy preserving. And in the end, you trace over the bath. Then you get a new state, and this is the way you want to do your state transformations within this resource theory. Then you can ask, well, if these are the rules of the game, then which transitions can I actually do? How much work can I, for example, extract from a state with such a scheme? And the first theorem that was shown by Horodetzky and Oppenheim was to give like a general mathematical, more or less, answer to this question for block diagonal states. So block diagonal states are just states that are diagonal, that you can diagonalize in the energy eigenbases. These would be states that do not have coherences between different energy levels. These will always be called block diagonal now. So what Horodetzky and Oppenheim have shown is that you can transform an initial state of that form to a final state if and only if the initial state thermo-majorizes the final state. So thermo-majorization is a criterion that you can decide by drawing a graph, a diagram basically. So you take your state, you look at the eigenvalues of the different energies, the different energy populations, and then you sort them in a particular way with this inequality at the bottom. So you sort them when you multiply them with the Boltzmann weights. And then to the right on your diagram, you put down the Boltzmann weights, and upwards you just put the probabilities. And then you get a graph. It's a piecewise linear curve that you get for every state. So never mind the details. Just roughly what's going on is that if you have to compare the curve of your initial state, compare it with the curve of your final state. And if the initial curve is above everywhere the curve of the final state, then you can do the transformation. And then we say that rho thermo-majorizes rho prime. Now, how can you now use, so I don't want to say much more details about this because you're not really using this. This is really just to give you an intuition of what's going on. But what do we want to now do with this? So what you can do, for example, is you can ask and find the answer to the question, like, how much work can you extract from some given state? So suppose somebody gives you a state sigma on your system A, and allows you to perform a thermal operation. But what you want to do is you want to raise a weight basically in the same time. So you want to gain energy. You want to perform work. Here in quantum thermodynamics, one way to model this is to say that we have an extra system W, which is sometimes called the work bit, that starts initially in its ground state, and you want it in the end to be in its excited state. So you lift it by some energy gap delta. And then you can ask, what's actually the largest possible delta for whatever I can do to the system, such that this can be done by a thermal operation. So you want to ask the question, what's the largest possible energy you can extract so that the left-hand side of this process thermometerizes the right-hand side. Yeah, turns out actually the best you can do is you can try to fully thermalize your system A. So what you want to do is you want to create the useless state gamma, the Gibbs state in the end, and this allows you to extract the maximum amount of work. And then you can try to mathematically just work out what this criterion gives you. And it turns out that the energy, the extractable work is given by a quantity called F0. So it's a version of free energy F, but not the usual free energy. So you can see on the slide, you can see a definition. You have to somehow sum up the Boltzmann weights for all levels that have non-zero population, and then you take the log. So this is just some quantity you can compute. It's called F0 of sigma. And this tells you how much work you can extract from sigma when you do this process just in a single shot, only once. Similarly, you can ask for the work cost. And this is in some sense the opposite process. You start with a thermal state, which is the free state of your theory, and you want to create the resource sigma via some thermal operation. And in general, you cannot do this for free, so you need work to do this. So what you then do is you say, I want to start with my work bit in excited state, let it fall down to the ground state. What's the lowest amount of work delta that allows me to do that? Then you can similarly work out the answer, and the answer will be, it's another version of the free energy. Again, it's neither F0, nor is it the standard free energy F, but it's a quantity called F infinity. I haven't written down the definition because it's really irrelevant for what we're doing, but you can already see here that there's a family of free energies with some index alpha, F alpha. We have two cases now. One gives you extractable work, F0, and the other one, the work cost F infinity. Now it's important to see that F0 and F infinity are very different from each other. In general, F0 is much smaller than F infinity, and the standard free energy is in between the two. So this tells you that in general, you have to invest a lot more work to create your state than you can actually get out from your state. So this is in some sense a fundamental microscopic irreversibility that you find in this resource theory. Now, if you don't just want to extract work, then you can ask a more general question, which is related to the second law. You can ask, what are the general state transformations that you can do within this resource theory? And what can you do if you're allowed a catalyst in the process? So what's a catalyst? Basically, a catalyst is an additional system that is involved in the process, but that doesn't change. So again, you have the picture from before. You have your initial system. In initial state, you want to transform it to a final state. You have a thermal reservoir that you're given for free. But now you have this additional yellow system here, this catalyst system that somehow takes part in the process and that you return back and catalyst. And then this is what your thermal operation does. It maps your initial state rho to final state rho prime. It does some unitary, and it also preserves your catalyst, sigma z, in its state that's the same initially and finally. Now, what Fernando Brandão and co-authors have shown in their paper is they have fully answered the question, like which set of transformations you can do within that scheme. Turns out that you can actually transform a given state rho to a given state rho prime if and only if all the alpha free energies decrease in the process. So we have a one parameter family of free energy like quantities F alpha, and they must all decrease. And if that's possible, then you can transform the initial state to your desired final state. So now this includes F0 and F infinity that I've shown you before. And as a special case for alpha equal to 1, you just recover the usual non-equilibrium free energy, basically just U minus Ts. Yeah. So in a way, this tells you that the second law of thermodynamics must hold. So the free energy F has to decrease in the process, but there are now many more second laws. Yeah? So all these other alpha free energies have to decrease. That's why the paper is called the many second laws of quantum thermodynamics. So this is the statement, and then you may ask, well, okay, but what's the relation to standard textbook thermodynamics? And this has been answered in several different ways, and one paper here is by several people, including also Nelly, who gave the talk on Tuesday. If you look at these alpha free energies, and now you say, let's allow a tiny bit of error in the state transition, which is indicated by the symbol epsilon, F alpha epsilon. And now let's look at many copies of your state, which means that you have rho tensor n. Then it turns out that the rate of this quantity converges to the standard free energy, to the standard non-equilibrium free energy for all alpha. So what this tells you in some sense is that when you go from a single quantum system to a large number of non-interacting or only weakly interacting systems or particles, then it's really only the standard free energy F, like U minus Ts, that remains relevant, and that tells you which transitions are possible or impossible. So this also tells you that the rates of the work cost and the extractable work get really become the free energy F in the limit. And so you recover in some sense reversibility and the standard textbook laws of thermodynamics in the thermodynamic limit from this resource theory. Okay, so this is in some sense the background. Now let me tell you about some work that I did that gives you an interpretation of the free energy F really only actually for single particles and single quantum states. So this builds on earlier work I did with, on the one hand, Matteo Lostaglio, who is also here, and then my students Jakob Schalau and Michele Pastina. And recall now first the scenario that I've just shown. We have seen that all these alpha free energies must decrease. And that was the scenario. Yeah. So we had a system that's transformed, and we had a catalyst that should be preserved. And now what you see is that the catalyst, in the end, you get rho S prime tensor sigma C. So you get the catalyst and the system in a product state. But you can consider an alternative scenario, which I did in this paper here, where you say, well, why not allowing correlations to build up or entanglement to build up between the system and the catalyst? Since the local state of the catalyst is assumed to stay the same, you can reuse your catalyst later on. So the correlations will not prevent you from doing so in many cases. Now, what happens when you allow this more general scenario? So this would be the equation that you have. You transform the initial to a final state. The catalyst stays exactly in its state sigma C, but your final state is now not a product state. It is some bipartite state of SC with local marginals rho S prime and sigma C. So when you compute the partial traces of your final state, you get rho S prime and sigma C. Well, then you can show, and that's what I did in this paper, that such a transition is possible if and only if the standard free energy decreases. So this is quite surprising because it gives you, in some sense, a one-shot interpretation of the free energy F. Yeah, you do this process for one copy of your state and you do it only once. And the free energy tells you whether you can do it or not. So here is a more mathematical statement which tells you a bit more like how the different quantities depend on each other. So you have initial and final states. They should both be block diagonal, but they can be arbitrary non-equilibrium states. And then you say for every epsilon, I want an epsilon good approximation of my desired state. So I want to create rho A prime of epsilon. And for every such epsilon, you find a thermal operation tau epsilon and a suitable catalyst such that this equation here holds, so that the result of your operation is your epsilon approximated state on A. Oops, sorry. Whoops, here I am. And it's exactly the same state of C. All right. Again, this gives you really a single shot interpretation of the non-equilibrium free energy, which is just given by this equation here. And as I said, this notation here means that when you look at your final state and you compute the partial trace over the catalyst, you get sigma A prime. You compute the partial trace over your system A, you get the state of the catalyst back. So you can think of a machine like in this picture, basically, that's really only working at a single quantum system at once. That's your system A. And it's transforming that to its desired target state. And then it's working on a new, fresh, new quantum system. And the catalyst will be reused at any step of the protocol. Okay.
Sorry, I just have one small question.
Sure.
So however, the free Hamiltonian is not necessarily preserved, right?
Say it again, what's not necessarily preserved?
The free Hamiltonian of the system.
So here, well, here we think of A having a fixed Hamiltonian HA and C carrying a fixed Hamiltonian HC. And then certainly there's a unitary map that's being applied. Now, what's usually not discussed within the resource theory is how you actually really in practice apply this unitary. Typically in physics, we think that you have to switch on some interaction, right? And you change your Hamiltonian for a while, and then you do your unitary and you change your Hamiltonian back. This is probably what you would do in physics, but that's not considered within the resource theory. Okay, the resource theory itself, yeah.
Yeah, no, sorry. I mean the final Hamiltonian, because in your notation you denote the final Hamiltonian with a prime, so meaning
okay.
it might be different. So I don't know. Yeah, that's...
Yes. So at the moment, I'm assuming that the final Hamiltonian is the same as the initial, but you don't have to do that. So you can have a more general framework. But then you should be a bit more careful when you talk about the Gibbs state, which one is it, like the initial or the final one and so on. And then you would have to be a bit more careful how you write things down here. But you can also treat this within the resource theory, this case where the Hamiltonian changes.
Okay, all right.
Yeah, I think it's even in a paper by Hordetsky and Oppenheim, a scheme where they do this. So I would refer you to that for more details, I guess. Okay. Now, so far I've only talked about a state transition, rho to rho prime, but then you can ask, now what if I have a work bit that I want to extract work, or I want to ask how much work I have to spend on the system? Then you can really, if you introduce this in addition, then it quite surprisingly, you can say, well, then you have a fluctuation-free work cost. So as long as your gap of your work bit, the energy gap is larger than the free energy difference, then you can perfectly do the transition, and the work bit will perfectly fall from the excited to the ground state without any fluctuations. Similarly, you can do work extraction when you go from the ground state to the excited state, and this can be done in an almost fluctuation-free manner. So as long as the delta, your work gap, is smaller than the free energy difference, then you can go from the ground state to almost the excited state, like basically to an approximation of the excited state that's as good as you like. And this is probably surprising because usually we think of work fluctuations in this context, but in some sense the fluctuations of the work are moved into the correlations that are building up. Okay. Right, so what I've told you so far was for block diagonal states. Now let me say a bit about what happens in the presence of coherence, because then new phenomena take place that are really interesting. And they also have to do with something that's of interest outside of thermodynamics, namely with quantum clocks. So thermal operations, so when we study coherence in this resource theory, then one very important fact is that thermal operations are what's called time translation covariant, or time translation symmetric. So this just means the following. Here, this u of t, this is just time evolution. Yeah, you have your state, you evolve it for time t. And then it turns out that it doesn't matter if you first do your thermal operation and then you evolve in time, or if you evolve in time first and then you do your thermal operation. So thermal operations just commute with time evolution. Now this has consequences for state transitions that you can perform. So if you want to transform rho to rho prime, now suppose that your initial state is incoherent. Incoherent means it commutes with its own Hamiltonian. So it doesn't have any superpositions of distinct energy levels. Now, if this is the case, then your final state must also be incoherent automatically due to this property of thermal operations. In general, if your initial state is coherent, then it's very hard to work out in detail what your possible state transitions are. And there's been many works, including this one, that try to say something about that. Turns out that free energy is then not anymore, even the many free energies are not anymore the unique indicators of a state transition. So this is really characterizing the possible transition. In this case, is really a hard and open problem with some preliminary results. I think for qubits, it's been solved, but it's still open in general. Now, here's some intuition why incoherent states will always be mapped to incoherent states. So suppose first, for the sake of the moment, that would be wrong. Suppose somehow we could map an incoherent state into a coherent state with a thermal operation. Now, what would that mean? Well, if rho prime is coherent and doesn't commute with its Hamiltonian, then it means that it evolves in time. It's not stationary, so it somehow evolves in time. In this sense, it's a bit like a clock. Yeah, so I can really think of that thing as like ticking forward when time evolves. And then the impossibility of this process, that you cannot go from incoherent to coherent, really just means the following. It kind of means that you cannot generate timing information, coherence, like for a clock, for free without having some initial timing information. So you need a timing resource to generate more timing information. You cannot do this for free. Now back to thermal operations and catalytic thermal operations. What does it say in this context? So we've seen that thermal operations are time translation covariant. So what does it now tell us when we want to map a system and a catalyst in this form? Well, suppose that really only the free energy would determine the possibility or impossibility of this process. If that's the case, then something else would have to be possible, something quite unlikely, namely a kind of broadcasting of coherence process. And here's a picture of that. So you could have a situation where you start your system in an incoherent state. Incoherent means it's stationary. So think of a clock that doesn't have a clock hand. That's your system. Your catalyst could be in some coherent state. This is like a clock with a clock hand. Then you would do a time translation covariant operation. And then you would end up with your clock being the same as before. The catalyst state doesn't change. You would have correlations between the clock and the system. And then magically somehow, your system would also acquire some timing information. So in some sense, this would be a way to take the timing information of your clock or your catalyst and to broadcast it to the other system without disturbing it locally. Now, is such a process possible? It seems unlikely, yet we will later see that there's a paper by Arberg, I will get to that, who shows that in some sense that's possible. But what Matteo Lostaglio and I have shown in this paper here is that as long as your catalyst or your quantum clock is a finite dimensional system, this kind of broadcasting of coherence is impossible. So you cannot do this. When you have a quantum clock and the quantum clock is finite dimensional, then it must degrade on every use in some sense, even when you do it in a clever way and you're allowed to build up correlations. we can even say more general statements. So instead of talking about time translations, symmetry, and coherence, there's a general theorem that tells you cannot broadcast any kind of asymmetry for any kind of symmetry group, as long as the symmetry group is connected. So that's like a general impossibility theorem for a repeated use of a quantum resource. Now, what are the consequences now of this for catalytic thermal operations? So what we would like to have is you would like to say, well, this transition here from rho to rho prime and sigma, and the catalyst stays the same, is possible if and only if the free energy decreases. But unfortunately, this is only true for block diagonal for incoherent states. For coherent states, it's not true in general. Now here's a new development that's quite interesting. So instead of the thermal operations, you can also consider another class of operations, which is called the Gibbs preserving maps. So Gibbs preserving maps are really all quantum operations that you can do as long as they preserve thermal equilibrium. So they map the Gibbs state gamma to itself. So every thermal operation is Gibbs preserving, but not the other way around. So there are many more Gibbs preserving maps than there are thermal operations. Now, Henrik Wilming, Rodrigo Gallego, and Jens Eisert have come up with a conjecture 3 years ago that now this equivalence is in fact true now for Gibbs preserving maps. So they conjectured that you can map an initial to a final state, rho to rho prime, with some catalyst involved by a Gibbs preserving map if and only if the free energy decreases. And indeed, this has just been proven. So I was hoping at some point to work on this and to present you a resolution of the results, but Naoto Shiraishi and Takahiro Sagawa have actually shown this now and proven this in this recent paper that has just appeared on the archive a couple of weeks ago. I think this is a really, really nice result and gives you an exact characterization what you can do with Gibbs preserving map in terms of the standard free energy. Okay, so this was so far about coherence and clocks and catalysis. Now let me conclude with an outlook on some ongoing work, which is closely related to it, which talks about two different notions of catalysis that you can have in quantum information or quantum thermodynamics. So here's the usual notion of catalysis that I've talked about so far. This I will now call a strong catalysis in some sense. Yeah, you have your initial state rho, you transform it to rho prime, and then you have this extra helper system, the catalyst, that's initially in state sigma c, and that's finally in the exact same state sigma c. Yeah. This is an obvious way where you can talk about using a system without using it up. You can reuse it. So you can then use your catalyst repeatedly on other systems. So here's like a diagram of that. So you do your operation once, you map rho to rho prime, you preserve the state of the catalyst, and this red wiggly line means that you have correlations now between the two systems. But then you can do it again. You can do the same transformation for another copy of rho s, just use your catalyst again and then do the same process and do that indefinitely. Now, however, you can also think of a modification of the scheme. You can say, well, why actually should the state of the catalyst be the same? All I really want is that I can still use it in the same way as before. So here's kind of a weaker scheme, a weak form of catalysis that you would also make us happy in some sense. You say, well, yes, I want my initial state rho and map it to rho prime. I have this helper system. The helper system is allowed to change, but I want to be able to reuse the other state nonetheless. So here's a picture how that would work. On the left, you transform rho to rho prime, and your state of the catalyst changes from sigma ci to sigma ci plus 1. Now that's a different state, but you can still do the very same things with it as initially. So you can do another thermal operation perhaps now. where now this new catalyst state helps you to transform rho to rho prime, and your state of the catalyst changes again to sigma C I plus 2. And then you can do it again and again and again, indefinitely, as often as you like. This would also be okay, and this would be suitably called catalysis. Now, what we've shown here in this paper is that for coherence broadcasting, this doesn't really allow you to do anything new. So even if you just demand this weaker form of catalysis, as long as your catalyst is still finite dimensional, you can still not broadcast coherence from a system to another system. And so you can in general compare weak and strong catalysis. And in a paper that I'm just writing up now, I'm proving a theorem which tells you in some sense that weak and strong catalysis are equivalent in all realistic situations. So these are situations where you say the catalyst states, so let me go back. So you have this sequence of catalyst states, the first, the second, the third, and so on. And as long as this set of catalyst states is in some sense fundamentally finally controllable, in this case, weak and strong catalysis will just be equivalent and allow you the same kind of transitions. So here's an example. An example is really where if your catalyst is finite dimensional. On a finite dimensional system, think of a qubit. You can really think of controlling and preparing any qubit state in your laboratory to arbitrary accuracy. So as you fix some accuracy epsilon, you can prepare and transform any qubit state to that accuracy as you like with finitely many resources, at least in principle. So, and the theorem applies to that case. And since the broadcasting that I've talked about is a special form of catalysis, this also tells you that a weak broadcasting of coherence is also impossible. But here's a famous non-example, and that's Arberg's paper on catalytic coherence. So this, in this paper, Johann Arberg has shown that in our language, weak broadcasting of coherence is actually possible as long as your catalyst, your helper system, is allowed to be infinite dimensional. Not only does it have to be infinite dimensional, but it's a ladder system where your catalyst state is spread over many energy levels, and it spreads further on every use. So you use it, it spreads out. You use it again, it spreads out even further. And again and again and again, and it spreads out even further. And you can see that at some point, you must exceed the limits of what you can control in a laboratory. So this would be a non-example, this example of a set of catalyst states that's not fundamentally finitely controllable. And in this case, weak and strong catalysis are not the same. And in particular, this weak form of broadcasting does become interesting in this case. So I'm still a big fan of Johann's paper. I think this is a great discovery, but I think you can show that this comes at a price, namely that the set of catalyst states that's involved in the long run must in some sense be hard to control, and in some sense, in this sense, perhaps unrealistic. Okay, I'm already at the end. So here's a bit summary. I've repeated, I mean, many of you will have seen that, how you can formulate thermodynamics as a resource theory. Then I've told you about work by Fernando Brandão and co-authors that tell you that you have fundamental irreversibility for work extraction, work cost in the single shot regime. And you also have many second laws in that regime usually. But I've shown you that when you allow correlations to build up, then you restore the usual textbook second law in the single shot regime. We've seen that coherence introduces additional constraints that cannot be quantified in terms of free energies. And reasoning about coherence is related to reasoning about quantum clocks, basically, where you use, in some sense, timing information as a resource. And in the end, I've given you an outlook on some work in progress on two versions of catalysis that turn out to be equivalent in many cases. So if you're interested, here's a list of references. I hope this third paper will come up soon. As you know, plans that something's out soon will usually take longer than one thinks in the beginning. But yeah, hopefully at some point this will appear. Okay, so yeah, thank you very much for your attention. Thanks.
Okay, thanks, Markus. Thank you very much for the very nice talk. So let's see, does anyone have any questions? Okay, maybe I can kickstart with one to get things going. I was actually kind of curious in the weak catalysis scenario that you mentioned. So do you have to assume that it is the same thermal operation every time, the gray boxes that you had there, or it can be different ones? And does that matter?
This is an excellent question. It can be different ones, in fact. Yeah, can be different operations. In general, in this context, you will have to, given some catalyst, you have to choose a suitable thermal operation. They both have to fit.
Mm-hmm.
So you want the freedom to change both at every time step. And the equivalence applies even then. You're allowed to change your catalyst at any state, allowed to change your operation at any state. And still this is the same as if you would use the same catalyst state and the same operation at every state.
I see.
Yeah.
Cool. So any questions? Actually, oh, okay, Camille, please go ahead.
Okay. No, yeah, maybe this is maybe a silly comment. I don't know. No, just to see again the result of Aber on the catalysis in infinite dimension. This remind me somehow of using a demon Maxwell. So, is there any one on a relation between catalysis and the Maxwell demon, or?
It's, yes, it reminds me also of Maxwell's demon in some sense, right? So you can say, well, if I have some version of Maxwell's demon and this demon is just allowed to accumulate more and more information and store it all in its memory, and I model the memory as infinite, then yes, I can violate the second law. So this already makes you perhaps suspicious that somehow you want to bound any kind of resources in some way to avoid this. Which is what in my last slide, actually, what I'm aiming at formalizing in this fine paper. Still, I think what Aberg did is a bit more subtle than that, because for a demon that just accumulates information, you can easily say, well, if I just quantify somehow the entropy of its memory, then I can see that this grows indefinitely. So I can quantify the resource that my demon is using up and see that it's using more and more of that. So it's like giving him an infinite resource or so, this demon. It's more subtle, and it's in Aberg's scheme, because it's not clear how you would quantify the resource that Aberg allows by having this ladder. Yeah, it's a so it's more, you cannot say, well, entropy is dumped into it or so. This is not something you can say. So what you want is some more general, I think, operational framework where you say any kind of catalysis should satisfy this and this and this to be realistic. And then you can say, well, that violates these conditions. But it's more subtle than for Maxwell's demon, I guess.
But Markus, let me ask, I mean, isn't it possible to kind of make a regularized version of this infinite ladder, like somehow like a harmonic oscillator with a very small frequency, and always work in this sort of limit where it becomes infinite? Wouldn't that solve the problem?
I think, yes, you can do it to some extent. And I think there has been some very interesting work on this. Even in Johann's paper, there's already a section where you say, well, let's at least have a lower bound on the energy and have a half ladder that's more realistic. And then I still think it's extremely interesting that you can do this for a while and you preserve exactly the operation of the catalyst. Well, I still believe, though I would have to ask more experimentalists or so, or people who are less mathematicians than I, how realistic that would be, because my guess is still that at some point you would run into limitations.
Mm-hmm.
And then we know from phenomena like embezzling, for example, that if you only allow cyclicity approximately and allow a little bit of wiggling and kind of a little bit of cheating in a catalyst, then you can immediately achieve a lot of cheating in some sense. So that's a bit why I think there will be problems of realization at some point, even fundamentally.
I see. I also actually have another question, going back to the beginning of the talk about this single shot interpretation. So to be honest, I didn't understand how the assumption that the system remains correlated with the catalysts, which that part I find quite reasonable, but how does that imply it's a single shot scenario?
Oh, yeah, that doesn't in itself make it more or less single shot than the other scenario before. So both scenarios, like first the one by Brandao that I've shown you and mine, they are both single shot, because you can say I have really just a single copy of my state and I want to do it only once, that I transform it to this other state. Or you ask, I have really just this one quantum system and I want to raise my weight and I want to have a probability of 99% that I can raise my weight in this one run of my experiment. Yeah. So in this sense, that's what single shot means. You don't want to average or say I do it 1,000 times and see how much work can I get in average.
I see. Okay.
But coherent, like correlations, yes or no, doesn't change that.
Okay, I understand that. I somehow misunderstood that. Okay, cool.
Yeah.
Any other questions?
I think there's a question in the Q&A.
Oh, there is, yes. So it's a question from Ivan Henao. So he's asking, thanks for the very interesting talk, Markus. I was wondering, you can probably read it, right? But I was wondering, the equivalence between weak and strong catalysis can hold for exact transformations? Because you mentioned an example about transformations up to certain accuracy. If not, does the error in the transformation changes as you repeatedly use the catalyst? In particular, would it decrease?
Okay. So yes, there's a lot to be said about exactness versus approximate transformation. I mean, let me see that I get this question right. So let me just read it once more. Yeah, okay. So first you can phrase this equivalence as applying to exact transformations. You just say, what transformations can I exactly do from rho to rho prime while exactly preserving the catalyst? And the answer turns out not to depend on what notion of catalysis you use. In both cases of catalysis, however, you can now say, well, I want to allow some approximation, but it's a bit subtle about what you want to allow. I think you should not allow an approximate to get your catalyst state back approximately. You want your catalyst state back exactly, because you somehow want to say you want to use it again, and it should be an exactly cyclic process. And we also know that you can have phenomena like work embezzling or things like this when you only allow that your catalyst, for example, is returned back in close to zero trace distance to its initial state. So the catalyst should be exactly preserved. But then you say, well, I want to transform rho to rho prime. There, why not allow a little bit of epsilon wiggling? Yeah. As long as I can make the epsilon as small as I want, that's okay. The fine print, of course, is if you want to make your epsilon smaller, then in some cases you need larger catalysts. So there's sometimes a funny trade-off between accuracy of your transformation and size of your bath or size of your catalyst. For example, when you want to extract work, when you say I want to raise a weight from exact ground state to close to exact excited state, you can never get to exactly the excited state, because it would basically violate a rank condition. It would mean that you take a mixed state and you basically get a pure state out or so. You have to approximate this, and there it turns out that the better you want to approximate this, the larger has to be your catalyst. So these are the subtleties that are behind all of the scheme. But I think the difference, to get back to your question, I think the difference between weak and strong catalysis doesn't matter for that particular question.
Okay, it's very interesting. And in the sense on weak catalysis, another thing that I was wondering was, so if you have the catalyst being reused to make multiple transformations, then the different systems, they will also become correlated indirectly, right?
Yeah, yeah.
Is that relevant, or does that play a role?
Yeah, so that's true. The other systems will also become correlated. And I think the answer whether that's relevant depends on what you want to do. I think macroscopically in standard thermodynamics, then you wouldn't really care so much about correlations between systems building up. Microscopically, or at least, the two scenarios that I've shown you would more or less collapse into a single scenario where just the free energy tells you what you can or cannot do and full stop. Turns out when you go into this nanoscale, this kind of, you get two possibilities, like what you want to mean by catalysis. And I think in cases where you want to have your single system and act on it repeatedly, then you need the stronger form of like this product catalysis that Brandau and others have introduced. But you can think of a system that's a bit more in the picture that I've shown you, where your first quantum system comes in, you act on it, it flies away. Your next quantum system comes in, and like in a collision model, or perhaps think of a biological machine and there's a stream passing by the biological machine or so. For such a machine, it would be perfectly suitable to introduce correlations because they wouldn't disturb what the machine intends to do locally.
Mm-hmm.
So then it depends on like, yeah, what's the figure of merit that you want to achieve in your protocol, and especially how do you want to combine the different system in which you act sequentially.
I see. So let's see. I think now we have a question from Marty. So Marty?
Yes. Do you hear me? Yeah.
Yes.
No. So I have actually, it's a very generic question or comment. So, but there's still a bit of time for discussion. So what I was wondering a bit, because we saw a few talks about catalysis. So a bit from outside, it seems like that as a community, we are getting to a very good understanding. And I was wondering a bit, are there still open questions that, because for example, there was this very nice conjecture that you mentioned, it was just solved. So I was just curious to know like a bit where the field is going over this specific question, right?
Yes. So I can think of two directions where you might want to go with this. One direction I think would be to ask, how would you realistically design a machine that does catalysis? Because so far the scheme is in some senses very unrealistic. In some sense, you need to have like a big bag. In the big bag, you have so many. You have 1 trillion catalysts, because for every state transition you have a suitable catalyst. So today you want to transform this row to that row prime, so you need that catalyst. But maybe an hour later you want to do another transformation, you need another catalyst. Perhaps there's a kind of, could there be a universal set of catalysts, a small set perhaps that you can use for state transitions? That's a question. Or when you allow correlations, what kind of correlations can you create? Can you, for example, avoid, you can make the correlation small, but can you avoid, can you make them Markovian, for example, that maybe the first and the second system become correlated, but when you trace out the second, the first and the third are decorrelated or so. So there's a large set of possible questions that you can ask. I think in quantum information, there are kind of fascinating questions, because what this also gives you is it gives you a one-shot interpretation of the von Neumann entropy, just information theoretically. And then you can ask, well, what about other quantities like the mutual information, for example, that appear in protocols like decoupling in quantum information? Is there a one-shot interpretation of this quantity when you allow catalysis in a suitably loose way in some sense? So if I would want to hype this, I would say, hey, maybe there's a complete new sector of quantum Shannon theory. Now, I'm not sure if that's true, but I still think it's a fascinating open problem to find more one-shot interpretation of standard entropic quantities.
Yeah, it sounds definitely interesting.
But it's very hard. I really tried for a while for the mutual information, but I couldn't even come up with a conjecture.
Yeah. Okay.
So yeah.
Okay. So thanks, Marty. We also have another question in the Q&A from Felix. In the single shot case, can anything be said about what happens if you allow to bring discarded but still correlated catalysts?
So Felix, do you now mean that I have used my catalyst, it's becoming correlated with the system, and now I bring that catalyst and also that system back so that the correlation remains, and then I'm going to do something new to that system somehow? So I think that's how I understand your question.
So Felix, you can probably talk now if you want. I don't know if it's let's see.
Okay. So these are good. So let me. I think the way I understand now Felix's question. So I would say the only thing I can say to your question is that in the scheme, in principle, you can make the correlations very small. So when you do your transformation in a very clever way and you use a clever catalyst, you can make the mutual information between system and catalyst less than any epsilon that you like. And this also means that you're in trace distance very close to a product state. So then when you now do new operations on system and catalyst, this implies in some sense that you're not very far away from the scenario that you would have if you actually had a product state. So I think that would allow you for a little while to act as if there were no correlations until they, at some point, they accumulate, perhaps. Yes.
Okay, so I guess if we have a little bit more time, there is also a question, again, more of a comment by Ivan in the Q&A. If I may add something, my intuition is that the accuracy in transformations will not be worse in weak catalysis, as Markus pointed out, because thermal operations involve infinite paths. For finite paths, I would expect that as the catalyst gets degraded, the error in the transformations probably would decrease.
Mm-hmm. Mm-hmm. It's quite possible. Yeah, the question of finite paths is very interesting. I think nobody has really studied too much of that. When your path is finite, and then you also want, say, your catalyst to be finite or so. So that's very natural. And what you're kind of pointing at here seems quite plausible to me. Yeah, I would have to think about that, but that sounds plausible to me, what you say here. Yeah.
Okay, great. So I guess if we don't have any other open questions, then let's thank Markus again for the very nice talk. Thank you.
Thank you
and
again.
I think this closes today's session. So Camille, I don't know if there's anything else you'd like to announce.
Yeah, no, nothing special. Again, the same thing as